It's just trying to identify, what I would tell you to do is if you're asked to give the name or the formula of any kind of molecule, the first thing always is to try and figure out, is it ionic or is it covalent? Because that's going to determine how you go about the naming. So disulfur tetrabromide, what is that? Ionic or covalent? That is covalent. Good. So that's covalent, and I know because sulfur is a nonmetal. So remember, you just look at the first element. If the first element's a nonmetal, then I know that it's going to be covalent. So then formula, what would I put? Yep, S2Br4. Tetrabromide, so tetra, remember, is 4. So with covalent, you always have those number prefixes. The number prefix tells you how many of each of the elements. So each element's going to have its own. Remember, if the first element is a 1, they won't put a number. You won't put mono. But if you just see like carbon or just see nitrogen as the first element, remember that means there's just one of them. So don't let that kind of throw you. But this one, disulfur, 2 sulfurs, tetrabromide, 4 bromines. So then looking at the next one. So K3PO4, ionic or covalent? Okay, I heard both. Covalent? Anyone? Ionic? Okay, so where's your Y? Where's K on the periodic table? Because remember, you just look at the first element. Where is it? To the left of the zigzag line, so it's a metal. If it's a metal, that means this is ionic. So look here, sulfur. This is a nonmetal. That's how I know it's covalent. Here, potassium, this is a metal. And that's how I know it's ionic. Just look at the first element in the periodic table. You always get a periodic table. And the periodic tables I use have the zigzag line, very obvious. Anything to the left is going to make this ionic. Anything to the right for the first element, and it's covalent. So I know that this is ionic. So with ionic, what is this one's name? K3PO4. Potassium. And then you got to remember that PO4 is what? Phosphate, not phosphide, right? If it was phosphide, it would just be a phosphorus. But phosphate, remember, is the polyatomic ion. So that, being that polyatomic ion, so you just use the whole name of the polyatomic. So this one is phosphate. Okay, looking at the next one, N3O6. Is this ionic or covalent? Covalent, because nitrogen is to the right of the zigzag line. That's how I know. So N3O6, how do I have to name this? Try nitrogen, whole name of the first element, and then hex oxide, first part of the second element plus IDE, but I have to use number prefixes with covalent. So whole name of the first element, and I know that looks kind of weird, try nitrogen, but it's always the whole name of the first element, first part of the second element plus IDE with covalent, but then you've got to add those number prefixes in. Last one, chromium nitrate, chromium 2 nitrate, sorry, ionic or covalent? Ionic, because chromium is to the left of the zigzag line. If the first element is a metal, it's an ionic compound, right? So now, this one's the one that, what do you have to do? To figure out the formula, you first write down the symbol. So what's the symbol for chromium? Cr. And what's its charge? It's a +2 because that's the Roman numeral. Remember, the Roman numeral tells you the charge. So that's a +2. And then nitrate. So this is not nitride. This is nitrate. So what is nitrate? It's an NO3 and has what charge? A -1. Okay? So those are those polyatomics. Remember the 7 that I gave you. So you just need to make sure you have those down as a list. You want the formula with its charge and the name so that you can use them. Don't forget to keep the charge in there because you don't want just the formula and then be like, I don't remember the charge. So you make sure you put formula and charge with each of those polyatomics and then the name next to it to help you do any kind of naming you got to do. All right. So it's not a 1 and 1, the charge +2 -1. So what do I got to do? I'm going to swap them. So how many chromium? Just 1, because remember this nitrate's a -1. So this is a -1. So that means I only have 1 chromium, but I have How many nitrates? 2, because the 2 from the chromium charge tells me how many nitrates. So if I have 2 nitrates, what do I got to add? Parentheses. Right? So I don't split up the NO3. Think of it as staying as one thing. Okay? The polyatomics do not split up when you do figure out their formula. So the NO3 stays as an NO3. If there's more than one because of the swapping, then just put parentheses around the polyatomic and put the number outside. So that 2, which was the charge on the chromium, tells me that I have 2 nitrates and I need to use parentheses. I don't have to use parentheses with single elements, only with polyatomics. Okay? So hopefully that is like bringing that up in your head. If it's like, I still don't got this, then you need to go back. You know that you can download like blank PowerPoints. You could like download chapter 3 PowerPoints that are blank and then practice them and then check your notes to see if you actually got them right. That would be a way of going back and trying to check. I did fill out all of the ones that we didn't do in class that are on the chapter 3 PowerPoints. There's like 2, maybe 3 slides that had questions about like ionic versus covalent, naming versus formula. And so I actually did all of those, finished them, and they're posted in the marked up PowerPoint. So if you have some blanks in your PowerPoints, you could do those and then check. So everybody knows like these PowerPoints that I write on, I post in Moodle. And they're posted as whatever chapter they are. And then it says marked up PowerPoint. So that's going to have my notes in it. So that way, if you missed a class or if you missed something that you're like, I think she wrote that down, but I forgot, you could always pull those back up in Moodle and look at them. If you miss a class, I record the lectures, so you can also always go back and watch the YouTube video. I try to crop out any of the downtime. So like if I give you time to do stuff, I usually try to pause the recording so that you're not like sitting there and it's just nothing going on and you have to try to skip forward. I do try to block some of those times out, but just trying to give you more practice. All right, so these ones are the ones that we finished at the very end of chapter 3. So if you see moles and grams, what do you need to know? If you see moles and grams, how many moles are in 243 grams of N3O6? What do I need to know? What is it called? I need to know the formula mass, okay? So if I see moles and grams, doesn't matter if it's asking for moles or asking for grams. If you see both moles and grams in the problem, then I know that I need to know the formula mass. So what is the formula mass? The atomic mass of 3 nitrogens and 6 oxygens. So it's the atomic mass of all of the elements in the compound. So I have N3O6. So you got to use your periodic table for this. Nitrogen, what is the mass of nitrogen? It's like 14.01, round it to a whole number. How many of them do I have? 3. So I have to take those 3 nitrogens and multiply it times the mass of each one. So that would end up being 42. So that's going to add 42 grams to the mass. What about oxygen? I have 6 oxygen, and each one weighs 16. Okay, so if you look, that one's 16.00. So that's 16. So when I do that math, it is 96. And now I just add them, okay? It is the mass of each atom in the formula. That is what the formula mass is. All you got to do is use the periodic table. So now just add these two and you get 138. That means there's 138 grams in 1 mole. That is like a unit conversion. Okay, so now I can go from grams to moles or moles to grams by using this formula mass. So now if I know 243 grams of N3O6, that's my known. So 243 grams times in a line. What's the unit of those 2? Which do I put on the bottom? Grams. Whatever you're given goes on the bottom in the first step. What's going to go on top? That's what I want to know, and that's moles. So you can do it in just a single step. What do I put in front of moles? 1. Moles gets the 1, and all of these moles will get the 1. And then grams I put 138. So I'm going to take 243 divided by 138. 243 divided by 138. And I got a really big, long number. 1.76086, 565, hold on. I can't talk right in the same time. Right? Grams and grams will cancel, so my answer is in moles. So that's entirely too exact. So how many significant figures in my measured value? 3. So remember that I'm always going to go back to the problem. Don't use the number of grams in a mole when figuring out how you round. You're going to go back to the number that's measured. So my measured is 243 grams. So 3, when you go to round, that means I'm going to keep the 1, the 7, and the 6. The next is a 0. So what happens to all of those? They all get dropped off, right? So my answer would be 1.76 moles. 3 significant figures within my answer. I keep that decimal place because it shows the size of the number. All right, so now the next one. So in the next one, I see how many moles are in 2.56 times 10 to the 24th molecules of the N3O6. If I see moles and molecules, now what do I need to use? What's his name? Avogadros. Right? So if I see moles and molecules, I don't have to figure out anything from the periodic table. I just use Avogadro's number. And this is, again, I'm just using it like a unit conversion. It'll let me convert from moles to molecules or molecules to moles, because Avogadro's number is that there are 6.02 times 10 to the 23rd molecules in anything of 1 mole. So you put your known value. You're always going to have your known value in the problem. So my known value is 2.56 times 10 to the 24th molecules. And I really encourage you to use the units. Keep the units. I see students are real bad about just putting like 2.56 times 10 to the 24th times in a line and leaving the unit out. If you put the unit, then you know to set them up so they cancel. And that's going to make sure that you divide when you need to and not multiply accidentally. So with this, make sure that you keep the unit. You don't necessarily have to keep the compound formula. You don't have to put the N206, N3O6, but you do want to keep the unit, because when I go times in a line, this tells me I'm going to put the given unit on the bottom. So I'm going to put molecules on the bottom. And molecules, what's going to go on top? Moles. Because my question is, how many moles? So my answer I want is in moles. Moles gets a 1. Moles will always get a 1 with these two. Molecules is the 6.02 times 10 to the 23rd. Now, it's just a matter of doing the math. And I will tell you, if you have a graphing calculator, when you divide exponents, you need to use parentheses. Okay? So if you're going to use your graphing calculator, make sure you put parentheses around your two numbers so that they get divided completely. If you have the old crusty calculator, if you have one of the old cheap $10 calculators, use that EE button. That is the button that's above the number 7. That actually puts your number into exponents, and it puts the parentheses in there for you, so you don't have to worry about it. So when I put this in the calculator, I'm going to put 2.56 EE, and those two little zeros pop up on the old calculators. Then put in your 24. So it should look like 2.56 with a little 24. Then hit divided by and do 6.02 EE with the 23. So when I hit equals, I get, I'm going to change color so you can see it maybe. So I got another number with a whole lot of things, 4.252491694 moles. Molecules and molecules cancel. 4.252491694. Anybody? Everybody got that? Okay. Anybody not get that? Okay. And that's what I would say. Like, I would go through and just like practice it a couple of times with your calculator. Make sure that when you put it in, that you're coming up with the right answer. So I can't keep all of these. How do I have to round this one? So you go back to the measured number. So 2.56, 3 significant figures. So I'm going to keep 3 significant figures in this answer. So you start with your 4. So I'm going to keep the 4.25. The next number's a 2. So what happens to all of those? They get dropped off. Okay, so those are going to all round down. So my answer is going to just be 4.25 moles. What if I want to go molecules to moles? So in this next one, I see molecules and moles. So do I need the formula mass or do I use Avogadro's number? Avogadro's number. If you see moles and you see molecules, use Avogadro's number. And so in this one, the number I start with, 0.045 moles times in a line. I have to bash my pen about this morning. All right, what goes on the bottom? Moles. Whatever you start with, put that on the bottom in the first step. So moles goes on the bottom, and what goes on top? What I want. What do I want to find? Molecules, okay? Because the question is, how many molecules? So I know that's going to be the number that's going to have to go on, or the unit on top. Molecules gets what? The big number, 6.02 times 10 to the 23rd. Moles gets a 1. So see how now again, moles and moles will cancel. So when I put this in the calculator, 0.045 times 6.02 times 10 to the 23rd. And I got 2.709 times 10 to the 22nd. Anybody not get that? I don't know if you have to use your parentheses in this one. Like if you multiply exponents, I don't think it bothers it. But if you divide exponents with a graphing calculator, you got to make sure you put exponents in, or the parentheses around those exponent numbers. Okay, can I keep 2.709? How many significant figures in that? 4. 2.709 has 4 significant figures, but in my measured number, I have just 2. Right, so there's only 2 in that number, so that means I have to go to my answer. I'm going to keep the 2.7 because those are the first 2 significant figures I come to. So what happens to the 0.9? They get dropped off. So my final answer then would be 2.7 times 10 to the 22nd molecules. Because moles and moles will cancel.
So when you get moles, you don't use the exponent, because for the last one I got the exponent at 46, but then now we use the exponent. You know what I did?
Yeah, I did use the exponent, 22.
No, on the one before this, 4.25. At the end of it.
That is because you didn't use parentheses. So go back and put it in, put parentheses, 2.56 times 10 to the 24th, parentheses, divided by parentheses, 6.02 times 10 to the 23rd, parentheses equals.
I don't know why I got that.
That's because, and it's because you left a parentheses out somewhere. I can promise you that. I can run through and show you when we get done. But I know that that's the one challenge when using a graphing calculator, like the fancy ones. Like you actually have to put in more data. And if you had an EE button, you could actually use that instead. And then you don't need parentheses. But you might have one on there. I mean, once we get done, like I'll pull this up and we can run through it just to see. All right, so the last one. How many grams are in 1.5 moles of MgOH2? That is magnesium hydroxide. So what do I got to use? Avogadro's number or formula mass? Formula mass. If you see grams and you see moles, then you've got to use formula mass. Can I use the formula mass that I figured out above? No, because it's not the same molecule. I got to figure out the formula mass of magnesium hydroxide. So, formula mass of MgOH2. So, MgOH2. So, magnesium, find it on the periodic table. Find its mass and round it. So, it would be, can't see that far away. 24, good grief. I have 1 Mg times 24. Okay, each magnesium, remember it's the number with the decimal on the periodic table. It's always the bigger number, and just round it to a whole number. That's the easiest way to go. What about OH2? I have oxygen. How many of them? 2. Remember, with the parentheses, everything inside is found by the number outside. So that's 2 oxygens, and each one weighs 16. So that's going to be 32. So I have 24 and 32. And then what about the hydrogen? Each hydrogen, how many do I have? I have 2 because it's OH2. So remember, the parentheses means everything inside is found by the number outside. So I have 2 hydrogens. Each one weighs 1. So that's going to add another 2. So now add these up. 24 and 32 and 2 is 58. So here, 58 grams is equal to 1 mole. So there, sorry, I wrote it down low and really small. 58 grams is in 1 mole. That's my formula mass. And now I can do the unit conversion. So if you see grams and moles and you know you've got to do the formula mass first, and now it's just a single unit conversion, write down what you're given. So 1.45 moles times in a line. Keep the unit. What do I put on the bottom? Mole. What do I put on top? Grams, right? Because the question is how many grams? So the unit I want goes on top. Grams gets what? The 58. Moles gets a 1. 1.45 times 58 gives me 84.1 grams. Everybody got that? Check your math, or actually check my math. How many significant figures in my question? 3. How many in my answer? I'm done. That one I don't have to round because the significant figures are already right. Okay? Yes?
So when you're trying to get the that's only time you would put like the 6 grams on top.
No? So look at the 2 middle ones. So notice where I put 6.02 times 10 to the 23rd depends on the problem. So like question number 2, I wanted to go from moles to molecules. I had to divide by Avogadro's number. But then the third one, I went from moles to molecules, and I had to multiply by Avogadro's number. So molecules will always get the 6.02. And whether it's on top or on the bottom depends on how my units get placed. And that's why I would put your number down, times in the line, then put your units in, then put the numbers in second. Okay? And then that way, you're actually like following the units to do this. So you know molecules will always get 6.02 times 10 to the 23rd. Grams is always going to get the formula mass. But if you set your units up first so that I know grams and grams cancels, or molecules and molecules will cancel, then that way you're going to put your numbers in correctly. Okay? Yeah, moles will never have 6. Moles is always going to get the 1, right? So notice in all 4 of those, moles is the 1, because it's really looking at the ratio of how many grams in 1 mole, how many molecules in 1 mole. So moles is always going to get the 1 in these. So grams will get the formula mass. Molecules will get that 6.02 times 10 to the 23rd. Okay? So hopefully it's a little bit of a refresher, a little bit more practicing. So let's go back and practice some of this. Okay, so now we want to be much more comfortable with naming organic molecules. And so the steps in naming, the first step when you get a molecule, whether it's written out as a Lewis structure or a skeletal structure or a condensed structural formula, however they have it written out, you always want to try and find the longest continuous chain of carbon atoms. And remember, that's not always straight in a row. So those carbon atoms can actually go down around the bend kind of thing. And hopefully in lab you saw this week that when you start to get more and more carbon atoms, you can fold them. They get this kind of zigzaggy pattern, but you can bend them, fold them around. They are not like in a straight line like we draw them. We just draw them this way because it's very convenient. So always find the longest continuous chain. You might have to start from every end on the molecule and kind of try different ways. Find the longest chain. That becomes the last name or the parent name. Like, you know, I'm a Carmichael. So that becomes the last name. It always goes at the end. Now I've got to go and find anything that's not hydrogen that's hanging off of the chain and name that. If there's a single carbon hanging off of the chain, it'll look like a CH3 or a carbon with 3 hydrogens around it. If it's a skeletal structure, it just looks like a funny little stick sticking off. But that is a methyl group. Because remember, one carbon is meth. But if it's a hanging group, then it's a methyl. Same thing with the 2 carbon group. So if you have 2 carbons as part of a chain hanging off, that becomes an ethyl group because 2 carbons is an ethyl. I will tell you we almost never have propyl, so we're not just forget about them. We're not going to do those. So then the other 4, those are used because they're really easy. Those are the halogens. Fluorine, chlorine, bromine, and iodine. You know that when they form a covalent bond, they only ever have how many bonds? 1. Because they're all in group 7. They all have 7 valence electrons, so they only share 1 pair. So they can be anywhere there's a hydrogen. You could also have a halogen. So they're kind of easy ones to name. If you're going to name them, though, you don't use the whole name. You use the first part of the name, and you add an O. So fluorine becomes a fluoro. Chlorine becomes a chloro. Bromine becomes a bromo. Iodine becomes an iodo. Okay? So once you've identified and named all of the hanging groups that are not hydrogens that are attached to the longest chain, then we got to number the chain. So we need to number the chain, and the reason is you want to always start from the end with the closest hanging group so that your hanging groups have the lowest possible number combinations. So what I do is I start from either end, and I just start coming in until I get to a hanging group. Whichever side I reach a hanging group first, that's the side I number from. Sometimes it doesn't matter. So remember, you saw that in lab yesterday, is like a 3 carbon molecule where there's something hanging off of carbon number 2. It really doesn't matter which side you numbered from, it would still be a 2. So sometimes you'll find that, but it's always good to check. Start from the edge, work your way in, carbon by carbon. The first one that you reach a hanging group, that's the side you're going to number from. And then the last one, you just list them alphabetically. So you would always list bromo before chloro. You would list an ethyl before a methyl. Okay, if they just get listed by their name alphabetically, which seems really weird. I would think they would do them by the carbon numbers, but no. Okay, I didn't make the rules up. All right, if I was an IUPAC member, I'd be like, wait. Be like, we don't like her, go away. All right, so just another note, if there is more than one of the same type present, so like if you have 2 methyls, instead of having to list the methyls separately, you can put them together. So instead of having like 2-methyl, 3-methyl, you can have 2,3 dimethyl. And that way it like puts them together. So for big molecules, that really does kind of help if there's a bunch of methyls hanging off of one. If there's 2, you'd use di, 3, you would use tri. In theory, 4, you would use tetra. We're not going to do any of those. Okay? All right. So now we're jumping forward. Well, we didn't do this one. We can do this one because I like this one. I think this one's kind of an interesting one. This, if you've got your PowerPoint slide, we named the one above. I need to slide. Look, it won't let me. Just stop. It's beeping at me now. Remember that all these dashes are hydrogens because carbon always has how many bonds? 4. Okay, and we're always going to be looking at alkanes, which means they're all single bonds. So you're always, if you're doing a Lewis structure, carbon will always have bonds up, down, left, and right. Okay, there'll always be a bond above, below, to the left and the right of every single carbon in your molecule. That is why when you see carbons on the end in a condensed structural formula, they're always CH3s because they're attached to the carbon, but then they're going to have hydrogen, hydrogen, hydrogen. Carbons that are in the middle of a chain will typically be a CH2 because they're attached to carbons on either end, and then there's hydrogens above and below. So if you look at this one, you tell me, what is the longest carbon chain that you see? So, I heard it. Said a little louder, it was right. 8. Okay, can you see 8? So there's 9 carbons in this molecule. Start at that end and follow it around. So start at this end and follow, if your pen will work. Do you see that? That is the longest continuous chain of carbon in the molecule. So it does not have to just be straight across. So always try, like, look and see. Does it go around a bend? Is it, if I go down, is it a longer molecule than just straight across? Okay, so 8 makes this a octane. So this is an octane. So I have now named all those carbons and hydrogens. You don't have to name the hydrogens. They're there. They have to be there to make the carbon have its 4 bonds each. So do you see anything that's not hydrogen that I have not circled? There's a carbon. Do you see the 1 carbon down here? Do you see that that one is not part of the chain? That one's a hanging group. So that one's sticking off of the chain. So I have to name that. That's a CH3. So it's called a what? That's a methyl. So now I got a number. So start from that upper left end and the upper right end, kind of count in carbons. Which side do I reach the methyl group first? From the right, okay? So notice if I start from the left, I have to go 1, 2, 3, 4, 5, 6 before I get to the methyl group. If I start from that upper right, it's just 1, 2, 3. That tells me I'm gonna start numbering my chain of octane from this side. This is carbon 1, carbon 2, carbon 3, 4, 5, 6, 7, 8. So that means my methyl is hanging off of carbon number 3. So see that 3? Tells me what goes in front of my methyl group. The number 3 doesn't mean that there's 3 methyls. The number 3 just tells me which carbon that methyl is attached to. So this would be 3 methyl octane. That's it. Do you see any others? Nothing else but hydrogens. So it looked really big, but ended up being just that it had only 1 hanging group. The real challenge with this one is just trying to make sure that you find the longest chain. All right, so let's do a couple of these ones. The top one, 4 carbons in a row, 1 carbon hanging off of carbon number 3 in the row. So longest carbon chain is 4. So you see I could go like this, 1, 2, 3, 4. Now if you look at other possibilities, there is this. That's 4. I could name it like this. That's not going to change because remember that these molecules, like it would end up being the exact same name because there's a little bit of rotation with single bonds. But if I said this, no, this would be wrong because that's only 3. So you want to make sure you find the longest. So simplicity-wise, sure, we'll go straight across. So that makes this a what? This is a butane. 4 carbons in the chain. This is a butane. Remember, methane would be 1 carbon. Ethane is 2 carbons. Propane is 3 carbons. Butane is 4. Those are the weird ones. Those are the ones that you've just got to like say them over and over and over again and look at them and like get those into your head. Because once you get past that, pentane, 5, hexane, 6, heptane, 7. Those sound like geometric shapes, or they're a little easier. They like match those number prefixes with covalent. So I don't think those ones are as challenging. But 1, 2, 3, and 4 are the weird ones. So methane is 1 carbon, ethane is 2 carbon, propane is 3 carbon, butane is 4. So I've named all those carbons. Once you circle them, now they're named. So you don't have to go back and do anything else with those. The only thing I have to name still is what? This one, right? So this carbon's not part of the chain. It's hanging off. So I have to name it, and it is a methyl. And it's going to be hanging off of which carbon? Carbon number 2. Anybody not see that? So if you start from the left and the right, do you see if coming from the right, I get to my methyl group sooner? So that means I'm going to number it this way. Okay? Those numbers are just to indicate where the hanging groups are on the longest carbon chain. So this is going to be a 2-methyl. 2-methylbutane. Try the one to the right. That is 5 carbons in a row, 1 chlorine sticking off of that first carbon on the left, and then coming down off of the 4th carbon are 2 more carbons. Longest carbon chain. Anyone? 6. Anybody not see that? So notice that that is longer than just going straight. That is the longest chain, 6. So that makes this a 6 would be hexane. Okay, so that takes care of all those. Now I've got to name anything that's not a hydrogen that's attached. So what do you see? You see I heard it? Chlorine. That becomes a chloro, right? So that's a chloro. Anything else? That 1 carbon, that is a methyl. Anything else? All the rest are just hydrogens. You don't have to name any of those. All you're looking for is non-hydrogen groups. So, which side am I going to number from? That left or the bottom right? The left, because where's the chlorine? On that first one, right? So when you start, you're like, oh, I got to go from this side because that makes my chlorine a 1, 2, 3, and that's going to make my methyl a 4, 5, 6. Okay, so the number is, the only reason you number the chain is just so you can indicate where the hanging groups are attached to the chain. Last thing, which gets written first, chloro or methyl? Chloro, because it's alphabetical. Okay, so I had 1 chloro, 4 methyl hexane. Now, when you do this in mastering, on my exam, I don't care if you don't put the dashes in, but in mastering and the way the IUPAC people are, they don't like to leave any spaces between numbers and letters because people might think they're 2 different molecules. And so instead, they use dashes. So they do a 1 dash chloro, dash 4, dash methyl, and then the last hanging group and the parent name, that becomes 1 word. So it would just be methylhexane, no space. Okay, so just know that. Like if you go put it in and you leave those dashes out, it might say incorrect. Make sure you put the dashes in. And that's all they want you to do is there's no spaces between. Any spaces have a dash. All right, so we'll leave that one for now. What about skeletal structures? So some students love these. Some students get them wrong all the time. Because the thing to remember with skeletal structures, every corner and every end is a carbon. Unless the line is going to a halogen. So for this first one, every end, so this is a carbon, 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 and this one is. So every corner in the zigzag pattern, every end is a carbon. But you see the line coming up to the chlorine? At the end of that line is the chlorine, not another carbon. So the only time the end of a line is not a carbon is if there's a fluorine, chlorine, bromine, or iodine on it. I mean, or an alcohol. I mean, there's lots of other things, but for our naming, that's the only ones you're going to see. So, longest carbon chain is, so that makes this a hexane again. Okay, and putting the C's in can sometimes help you like see it better. Now remember, all those C's have what else on them? Hydrogens, because carbon always has 4 covalent bonds. So those N carbons are CH3s. Middle carbons, like the one on the 3rd, 4th, and 5th carbons, those are CH2s. They're carbons, they don't draw the hydrogens, but remember they're there. They are there to make sure that the carbon has its 4 covalent bonds because this is a stable molecule. Okay, so we named this right? So that's the hexane. So the only thing hanging off is a chlorine, which is a chloro. And then which side am I want to number this from? Left or right? Left. Can you see that the left is closer to the chlorine? So that is the side that I would start my numbering from. 1, 2, 3, 4, 5, and 6. So this is going to be a 2 chlorohexane. I don't know what that is. 1. Okay. And you could put like 2-chlorohexane, all one word. Let's try the one on the right. So again, 1, 2, 3, 4, 5, 6. So your zigzag has 6 lines. So if you don't have the PowerPoints and you're just drawing them, do 6 lines as your zigzag. Off of the middle point pointing down, put a line, next one a line, and then one going up. You can go back in. Now notice there's no fluorine, chlorine, bromine, or iodine. So that means every end and every corner are carbons. So how many carbons total do you have? 1, 2, 3, 4, 5, 6, 7, 8. Total. So if you put a C on all of those, what's the total? 10. Does everybody see 10? So that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? Every end and every corner. So this would be a 10 carbon molecule. But when you go find the longest carbon chain, what do you see? 7. So that makes this a what? Heptane. Like a heptagon. So heptane is 7. So that means I've named all those carbons, the ones that you circled. Now those are named. So I've only got to name the ones that are like sticking out. So this is a what? That's a methyl, right? So it's a carbon, but remember it would have 3 hydrogens around it. So it's a CH3. So a single stick sticking out is a methyl. So then what's this? That's a methyl. And even this. You see that all of those, we've got 3 of them. They're all methyls. They're all just a single line sticking up. So now I got a number. Do I number from the left or the right? From the right. Because this is carbon 1, carbon 2, carbon 3, carbon 4, 5, 6, and 7. So that means that my methyls are on carbons 2, 3, and 4. So that's the numbering. The numbering's just so that I can tell where they are. So since they're all the same, I can put them together. So when you put them together, you put each number in order. So this would be 2, 3, 4, and then dash. And since there's 3 methyls, they tell you to say tri. So you use a number prefix with this. So this is trimethyl heptane. No spaces between the numbers, just commas. So 2, 3, 4, dash, trimethyl heptane, sorry. So really it is just this practicing. So I'm going to leave these 2. I want you to practice those ones because that one is a common one that people don't know where the carbons are. So practice those. We'll look at those ones next time. What if you have this? Or if you have a ring, you always call it a what? A cyclo. And it's named by the number of carbons in the ring. So looking at this first one, the parent name is the number of carbons in the ring, and you use the term cyclo. So it's a cyclo what? So you first, instead of there's no longest carbon chain, if there's a ring, the parent name is the number of carbons in the ring with the word cyclo. So this is a cyclohexane. So if you see the term cyclo, you know you're going to do a ring, and whatever the number is or whatever the term after the word cyclo, that's going to tell you how many carbons. So cyclohex, well, I got to do a ring of 6. Cyclopentane, I know I got to do a ring of 5. Cyclooctane, I know I got to do a ring of 8. Okay, so this is cyclohexane. So I've handled all of those. There's only one thing hanging off of this, and this is, what is that? It's I heard it. It's not a methyl, because a methyl, remember, would just be a CH3. This is a CH2, CH3, so one group hanging off with 2 carbons is a ethyl. It's the only one, so I know it's ethyl cyclohexane. What about numbering? I got to number the chain. If I want ethyl to have the lowest number, where do I start numbering? At the ethyl. just start on the hanging group, right? So make the hanging group number 1. So you could go either direction, don't really care, because it's not going to change anything else because there's only one of them. So I don't really worry about that. I just know that this is then 1-ethyl cyclohexane. But look at the one that's on the right. So that is a house. I tried to draw it more like a Lewis structure would look like. So what would you say that is? Yep, so this is a cyclopentane. So that names this, 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 and that. So then, if you look, are there any non-hydrogen groups? What are they? So you call those chloro and chloro. Okay, so I have 2 chloros, so I know I'm going to end up calling that a what? Dichloro. Remember, because that's going to tell me that I know I'm going to have a dichloro, so I got to number this. So again, just like with ethyl, where you start numbering, you're just going to pick one of the hanging groups, and then you want to go the direction so the next hanging group has the lowest number possible. So which one would you start with? The top one or the bottom right? Okay, so we're going to start at the bottom right. So this is carbon number 1. Which way would I start numbering? Would I go up or to the left? Up. Because this is carbon 2, and that's going to give me carbon 3. See, if I went like clockwise, then my second chloro would be on carbon 4. So I always want to like number towards the closest non-hydrogen group if there's more than one. If there's only one, it's 1. But if there's 2, then you want to start numbering so that you get the lowest possible numbers. And you notice if I had numbered it the other direction, would that have changed my answer? If I said this one's 1, 2, 3, do you notice that that wouldn't change it? Either way, one is going to be a 1, one is going to be a 3, because they're chlorines that are 2 carbons apart. So this one is carbon, you said carbon 3, carbon 1. So now I'm going to write this as 1, 3, and then dichlorocyclopentane. Just means there's a cyclopentane with a chlorine on carbon 1 and a chlorine on carbon 3. What's this last one? Looks like a funny duck. So that's a skeletal structure. So what's an easy thing to do so that you can make sure you count them all? Everywhere there's a corner, everywhere there's an end, what do you put? Yep, put a dot or a carbon. So you can go in and fill this in. I heard it, so that means the ring is a what? It's a cyclooctane, right? So if you count all of these carbons, do you see that there's 8 going all the way across? So that makes this a cyclooctane. So what else do I have to name? What are those lines sticking out? This is a methyl. And this is a methyl. And they would be on carbon number 1. Because remember, you start where there's a non-hydrogen group hanging. And that's the only one, so you don't even have to make any decisions. So this would be 1, 1. And what do I write that as? If there's 2 methyls, it is dimethyl. 1,1 dimethyl cyclooctane. So try to give you like that first one's like a condensed structural formula, the cyclohexane. The second one is kind of like a Lewis structure. The third one would really be like what they call a skeletal structure. Doesn't have anything, it's just all of the lines. But those are the different ways you could see them drawn. So now I want you to draw them. So I want you to draw 2-methyl 3-chlorohexane. How are you going to start? Like, what do you always put down first? the parent, right? So you look at the very last name, and it is hexane. So what am I going to put? 6 carbons in a row, okay? And you don't even have to do them in some strange position. You can just put 6 carbons in a row. So you can go, let me change. 1, 2, 3, 4, 5, 6. There's hexane. Boom. Okay? So these carbons are all going to have what? Above, below. Unless we have the non-hydrogens, which we got to put those on. But remember, I know that these carbons, if I'm doing a Lewis structure, boom, 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 right? I know that there's going to be bonds above, below, left, and right. So you can put all the little dashes. Second thing now, you can number it. Okay, most people number left to right because that seems like a normal order, kind of like reading. If you want, you could go right to left just to try and like mess with my head, doesn't matter. So this is carbon 1, carbon 2, 3, 4, 5, and 6. All that's doing is just numbering the chain. And so now, where do I put the methyl? Hanging off of carbon number 2. Okay, so that means that I'm going to have a methyl group, which remember is a CH3, hanging off of carbon number 2. Where am I going to put the chloro? On carbon number 3. So I could put it down below or I could put it above. I could put the methyl group above or below. It doesn't matter as long as the methyl is on carbon number 2. As long as the chlorine is on carbon number 3, it doesn't matter if they're both above, both below, one on either side. I just did it like this because I think it's a little easier to fit everything. Are we done? Yeah. Right? You've done everything. There's a 2-methyl, there's a 3-chloro, and you got a hexane. So all of those empty dashes are what? Hydrogens. So you can have the fun of adding them all in. So some students are like, I don't like doing all those hydrogens. So you could take this and make it into a condensed structural formula. So if I was going to do the condensed, remember that's each carbon and what's around it. So what would carbon 1 look like? How would I write carbon 1 in a condensed structural formula? I'd say it's a CH3, right? Because that's a carbon with 3 hydrogens. The next one, carbon 2, has how many hydrogens? Just 1, right? You see carbon 2 has an H up, but then coming down is a CH3. Then carbon 3 would have how many hydrogens? 1, so it's a CH, and sticking up it has a chlorine. But now 4 has CH2. 5, CH2, and 6, CH3. So that's kind of like the condensed structural formula. Any non-hydrogen groups would just hang down or hang up, either one, doesn't matter. They would just be attached to the carbon they belong to. So in this one, there's a CH3 off of the second carbon, there's a chlorine off of the third. All the other ones have to have hydrogens in order to make their total number of 4 bonds. What about a skeletal structure? How many lines would I make for hexane? Think. 5. Remember we talked about that last time. I said if you look at skeletal structures, because it's the bonds between carbons, if I have 6 carbons, I'll have 5 lines. So you just go 1, 2, 3, 4, 5. Now if you go back and count 1, 2, 3, 4, 5, 6, you can see 6 ends or corners. That's hexane. So if I wanted to put a methyl group on carbon number 2, which one on mine, where would it be? Yep, that first point right here. Oop. And what would it do? It would just stick up like that. That's a methyl. Do you see that that's on the second carbon? Because the first carbon is the one starting from the bottom. Then the second carbon would be coming up. So what would I stick off of the third carbon? I just hang down. I love this 10. I really do. 1, 2, 3, 4, 5. Hanging down, I'd have a chlorine. So that, the Lewis structure is the top one. The middle one is a condensed structural formula. The bottom one was how you would do a skeletal structure. I don't care which one you do. So on the test, if I give you this and ask you to draw it, you can draw either one of them, any of the three. You don't have to draw all of them, whichever one you prefer. Okay? But always when you do this, what you put down first, put down the longest carbon chain. Then you can number it and then just attach the non-hydrogen groups to whichever carbon it's listed as belonging to. So this one, how many carbons do I have to do in this one? 10, because it's a decane. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Decane, 10 carbons. So remember, I know that then I got dashes up and down on either end. You get really tired drawing them after a while. So now, how am I going to put my non-hydrogen groups? On the 7, what will come off of number 7? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 7. I'll have a what? What is that? It's a CH2, CH3. So this is like in Lewis structure form. That's an ethyl, and I just counted 7 carbons over and put it on. What else do I have to put on? Carbons 3 and carbon 4, I'm going to put a fluorine, 1 on each. Okay, so this is a fluorine, and this is a fluorine. Does it matter that one's up and one's down? No. As long as there is a fluorine on carbon number 3, it could be down or up. Either is fine. As long as there's a fluorine on carbon 4, down or up, either is fine. That's it. All the rest of those are what? Hydrogen. So if you were going to draw the Lewis structure, I'm not, but if you were going to do this, you would have to turn around and put hydrogens above and below any spaces that are still empty, right? So what's the condensed structural formula? So you tell me, condensed structural formula, what's starting from the left? What's that first carbon? CH3. Second, CH2. Third, CH with a F coming up. And then 4, CH with an F coming down. Then 5 and 6. Now 7, CH with the CH2, CH3 coming off of it. Then 8 and 9. And then 10 on the end is always CH3. Does everybody see that? Can you count those and see why those hydrogens are where they are and why? Carbon has to have 4 covalent bonds, so you fill in those hydrogens so that carbon always ends up with 4. Zigzags, way easier. How many lines in your zigzag? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. See? Done. So now I'm going to put a fluorine on what? I'm going to put a fluorine here and a fluorine here. Does everybody see that that is carbon numbers 3 and 4? And then what else do I have? Keep going. 1, 2, 3, 4, 5, 6, 7. So down here is my 7. How do I do an ethyl as a skeletal structure? Yes, it's like a line with a bend. So you come down and then put a curve on, put a bend on it, because that shows 2 carbons, right? Every bend is a carbon, every end is a carbon. So that's an ethyl group. Done. See how much faster? When you get really big molecules, that is why you start to see skeletal structures drawn more when we start talking about like fats and oils, because you have 16, 18, 24 carbons in the chain. And it's just so much to sit there and draw CH2, CH2, CH2 all the way across. So that's why big molecules, skeletal structures are much more commonly used. Okay? So who thinks that's a little easier? Yeah. I think it's easier because all you got to do is make sure you look at the last name, lay down the carbons, and then just hang them off of the carbon they belong to. Okay? When I ask you to do this, you'll have the option. You can draw them as a skeletal structure, a Lewis structure, or a condensed. Doesn't matter to me. So you'll have room to do any of those. Whichever one you're the most comfortable with, but just practice them. When you have to do this in mastering, oh, it's a pain in the neck. When you have to do this in mastering, Here's the steps to do, because I have students that are like, I tried to do that chem draw and there's carbons everywhere. Like every time I click, it would make water molecules, there'd be carbon. It was all over the place. I don't know if you've tried it yet, but it can be like, you're like, how do I do this? First thing to do is lay down your atoms. Okay, so like if I had to build this molecule, so if I had to build 3,4-difluoro-7-ethyldecaine, what I would do is I would click on the carbon and I'd go click, 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 click across and put 10 carbons across. Yes, they might look like CH4s. Don't let that bother you. Just lay the carbons down. A lot of time the ChemDraw tries to put the carbon with hydrogens to give it automatically 4 covalent bonds. That's fine, okay? So lay them all down, then put your fluorine, 1 fluorine above carbon number 3, 1 fluorine below carbon number 4. Then put your ethyl, so what, below carbon 7, put 2 carbons going down. Then go to your bonds. So there's like, you can have single bonds, double bonds, triple bonds. Don't worry, you only have to do the single bonds. So it's like on the left side, you can choose the bond, just choose single bond. Then you take your mouse, when you hover over a carbon, it'll turn green. It'll like highlight, left click, and then drag to form a bond. So that'll actually link the 2 carbons. Then when you let go, you'll have a line. Then hover over the next carbon, it'll glow green, left click, slide, let go. And that'll form your second bond. So it'll actually do this, connect all of your carbons, connect your fluorine to your carbon, fluorine to the other carbon, connect those carbons of the ethyl, and when you get done, it's all right. But the first thing to do is put down your atoms, then form your bonds. Okay? Because that's like, if you just try to like form them and connect them at the same time, you just end up laying carbons everywhere. It's really like craziness. Like, you're like, why there's so many? Then you have to just clear your screen and start all over because you're like, I'll just work on this later. It's really not that hard. Just make sure that you do it in that order. Okay? All right. So here's another one. We'll do these ones next time. Like I've left a few off because we'll go back and do a practice next time, but I wanted to kind of run forward to get through one more topic. Oh, and I forgot to bring them. Okay, we'll still talk about them. So this is the only thing, like you were in lab yesterday. In lab yesterday, we talked about naming, we talked about drawing, and we talked about isomers and chiral carbons. We like kind of did that. This is the only part that you don't talk about in lab. So this one's a little bit different. So I told you organic chemistry is like a 2-semester class. And you're like, why is it 2 semesters? This doesn't seem too bad. Well, organic chemistry includes all of the things that carbon can do. So remember that carbon, yes, carbon can form 4 single bonds, right? Those alkanes like methane, ethane, propane. But carbon can also form double bonds. And so if that happens, then you have, and I can't stand this because they're too small. We can go through them this way. So if it has a double bond, right, like this, those are called alkenes. So alkanes are when carbon all has single bonds, but carbon can actually exist with double bonds between the carbons, and it can still form a big long chain. If there's a double bond, even one, then they say that that chain is unsaturated. So remember last time I told you with alkanes, they sometimes call them saturated hydrocarbons or saturated fats and oils, saturated carbon chains. If they're all single bonds, if there's a double bond, then they're considered unsaturated. So they give you their examples. So like cholesterol, testosterone, estrogen, they've all got double bond carbons in their molecules. Ethene is one of a molecule made by fruit as it ripens, and it actually, that's why like one banana, if you put a brown banana in with green bananas, all those bananas will ripen faster. That's because of this chemical molecule it's given off by ripening fruits. There's even triple bonds. They're not very common. Remember when you tried to build a triple bond in lab when you did HCN? It was like, trying to like get that third bond on was really tight. These triple bonds, they call them alkynes. Okay, so all single bonds are alkanes. If there's even one double bond, it's an alkene with an ENE at the end. And if there are triple bonds in the molecule, they call them alkynes. They're not very stable, so they say that alkynes are more reactive. And it's really because those double bonds is too many electrons trying to be crammed between 2 atoms. So one example of a alkyne molecule is the toxin that's made by the little tree frogs that live in South America. So these little tree frogs are really bright colors. They're like bright orange, bright red, bright blue, and nothing touches them. Okay? The animals like walk by, nope. They're like, that's like that bright color. You would think, why don't they get eaten all the time? They actually secrete this toxin onto the surface of their skin because they're frogs, so their skin damp, wet, kind of slimy. And so this, if an animal picks it up in its mouth, it's actually a nerve toxin, so it causes paralysis. So the animal's like, look, a frog, picks it up, boom, falls over. So that's why the little frog's like, doo, 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 doo. So the frogs actually do quite well, and they can be bright colors because nothing eats them. So they are pretty rare in nature. They are pretty reactive. In fact, for a long time, people that lived in areas where these frogs were, they would take arrows and rub them on the back of these frogs. Like you'd hold the frog with a stick and rub your arrow on the back. And then when you actually like shot a deer with your arrow, what would happen to the deer? Yeah, it'll paralyze them so that they don't, if you hit them with the arrow, they're going to drop. Then you just cut out that area where the arrow was because you don't want to eat that because you don't want to fall over. And so instead, but this was like a really easy way for hunting. So it made them much more successful at hunting, recognizing that there was something on this frog that nobody needs to touch. Okay, just sort of an interesting one. I kind of liked the picture too. One other way that you might see carbon atoms, if they're a cyclo, and it only happens if you have a ring of 6. So notice this looks like a cyclohexane. So it's a ring of 6. If there are alternating single and double bonds, they call that an aromatic group. So benzene, which is a component that you find in gasoline, this, and used in a lot of different solvents, that is an aromatic compound. So looking at the ball and stick structure, you kind of see this double bond. Looking at it this way, what's really interesting is that this molecule, those single and double bonds can actually switch. So they can be like double bond, single bond, and then they can kind of switch places. So this actually creates a pretty stable molecule compared to most double bonds. You will sometimes see these two written. You'll see a molecule, don't be surprised if you see a molecule that looks like this, that looks like the cyclohexane, but instead of having that single and double bonds, it has this weird circle in the middle. And that's because those single and double bonds kind of flip back and forth between the carbons, and that's to sort of show that. They call it like resonance. So there's one, the other, and then that's what you might see, is that cyclohexane, alternating single and double bonds, and then having that little circle in it. A lot of plastics are made with these. They're called aromatic rings or aromatic compounds. They originally called them aromatic because they're kind of stinky. So like benzene, like a smell in gasoline, and in some of your like solvents that you use to dissolve like oils and things. So they were smelly. So that's how the term aromatic ended up coming into play. But those are these types of shapes. This is shown in pharmaceuticals. So if you kind of start looking, you're like, oh, I can see some aromatics that are in there. I can see some of these 6-membered rings. Some just have a double bond, but some have that alternating single and double bonds in them. So this is like morphine, oxycodone's in there, naloxone, tramadol's in there. These are all like the opiate pain meds. Okay, so we said alkanes. Remember, you can remember this because these are all single carbon-to-carbon bonds. And these are the ones we've been practicing naming. Alkenes, the ENE is when you have a double bond. Alkynes are when you have the triple. And then an aromatic is if you have a cyclohexane, but it has this alternating double and single bond arrangement. So instead of it being called one of the others, they call it an aromatic. These groups are not just carbons and hydrogens. So hopefully you get the idea why there's 2 semesters in organic chemistry, because we're not going to name them, and we're not really going to talk about them much more than just pointing them out. If on a carbon chain you have an oxygen with a hydrogen, that is an alcohol. So it's not a hydroxide, which like you've been thinking about, because remember hydroxides would be metals and nonmetals. This is an alcohol group. So this first one, 2 carbons, this is an F, and it's got an alcohol, this is ethanol. Okay, so ethanol is what you commonly think of when you think of alcohol. So this is what you find in distilled spirits, or you find in beer and in wine. So in this, just seeing just this OH hanging off of the carbon all by itself, there's no nitrogens or oxygens around attached to that carbon. It's just called an alcohol. Aldehydes, on the other hand, are when you have an oxygen on the end of a molecule and it's got a double bond to it. So this, when you see a carbon with a double bond, oxygen hanging off the end of a molecule, that's an aldehyde. If you took an aldehyde and an alcohol and like put them together, then you can really make what they call a carboxylic acid. So do you see how a carboxylic acid kind of looks like a combination of the two? So that's the challenge in trying to pick them out. So alcohols and aldehydes, if there's nothing else on the carbon, then those are them distinctly. But a carboxylic acid is when you have a carbon on the end of the chain or the end of a molecule. It's got a double bond oxygen and an OH. So those 2 oxygens on there, that's going to be the carboxylic acid. The next 2. So the next 2 are the amines and the amides. So amines and amides, they have what? What makes them different? They have nitrogen. So the first one, the amine, has a nitrogen. There's no oxygen on any of the carbons around them, just the nitrogen. The last one, though, is the amide, and that one has that double bond oxygen. So what we're going to do next time, so we'll do a couple of examples, but then I have molecules like this. So if you look at this molecule, you're like, holy cow. Okay, so we're just going to go through and label functional groups that are found in these molecules. You are not going to have to name this, so don't like have an attack. Okay, you are not going to have to name this molecule. It's really just a matter of picking out functional groups. And I actually have a handout that you can use on your exam that lists all the functional groups and what the molecules look like. So it's really a matter of practicing to get more familiar with them. Okay, so we'll finish the groups because I still have to talk about these ones. We will finish those next time and then we'll do some practicing. I opened chapter 3's post-lecture homework because we hadn't done moles and molecules and gram, formula, mass, gram calculations. So if for some reason you didn't finish chapter 3, make sure you get it done by Sunday. Okay, you can go ahead and start working on the chapter 4 ones as well.